Right, so we have a raft foundation which is sitting on a layer of sand, and beneath that layer of sand there is a layer of clay, and the clay itself is sitting on chalk. Beginning with a schematic diagram of the problem, we have the ground level, that is my GL, ground level. I have a raft foundation which happens to appear at an embedment depth, so there is a bit of excavation. Okay, happens to have some excavation. The raft foundation, the dimensions are known. That's 27 meters by 18 meters. And then the embedment depth is 3 meters. And then I have 6 meters of sand. That's all sand. So I have 6 meters of sand. It's not really to scale, so, but yeah, does the job. And the groundwater level is standing at 6 meters below ground level, so somewhere here. This is the groundwater level, and the groundwater level is standing at 6 meters below ground level, hydrostatic. Beneath the sand layer, I have a layer of clay, soft clay, about 7.5 meters thickness. Again, not to scale. .5 meters, which is sitting on a permeable layer of chalk, and that is your bedrock. I have some useful information which will be used in analysis, so let's put them on the board. We have the contact pressure, which comes from the superstructure, and that contact pressure is equal to 215 kPa or kilopascal or kilonewton over meter square. Then I have the bulk density of sand above groundwater level, the bulk density of sand below groundwater level. So for above groundwater level, I have rho, that's bulk density, 1976, typical of unsaturated sand, kilogram over meter cube. And then I have same parameter for sand below groundwater level, or saturated sand. (2138). kilogram over meter cube. The specific gravity of sand particles is known as 2.65, again typical of quartz. The water content of sand above water level is 8%. And the void ratio of sand, that is the average void ratio of sand, irrespective of its whereabouts, in reference to groundwater level, is 0.45. The bulk density of clay, that saturated bulk density, is measured and given as 1920. Again in kilogram over meter cube. For the clay layer, I have the slightly higher specific gravity, as it normally happens, 2.7. And the average coefficient of consolidation, that is average coefficient of consolidation of 0.0253 millimeters square over second. What I have is a diagram, and we have this diagram on the question brief, a diagram and a table which plots and relates the coefficient of compressibility, that is m sub v, against the effective pressure. It's something like this. Now we'll use this value for our analysis. So we have the, let's say, the variation of m sub v, coefficient of volume compressibility, in meter square over kilonewton, as an available data. We have a number of questions to tackle. Let's look into our questions. Question 1. We are after the total expected consolidation settlement for the center point of the foundation. Total value of consolidation settlement for the center of our raft foundation. I will look into the second part and third part later on, so let's begin with the solution in red color for part 1, and then we'll move on to all further parts. Right, by looking into this question, you can see that, well, you have some data which is coming from the item to test, but you do not have the variation of void ratio versus log sigma dash. And for that reason, you cannot say whether your soil is over-consolidated or normally consolidated. By soil, I mean clay. Because sand does not have much consolidation, we ignore that. We can't say whether our clay soil is over-consolidated or normally consolidated. We cannot determine the pre-consolidation pressure or the slope of the over-consolidated swelling line and normally consolidated verging line. These are C sub S and C sub C respectively. So you can see that I cannot possibly make use of my main method or the first method that we are familiar with. But there was a second method, and that second method tells us that's delta H. that is the consolidation settlement, is equal to m sub v, coefficient of volume compressibility, times the h, that is the thickness of your soil layer, multiplied by delta sigma. And that is the change in total stress, and at a very, very long time, the change in effective stress, which is what we are interested in. Now, it's a very simple equation, I agree with you, but the problem here is that we do not have one single value of m sub v. M sub v really varies with sigma dash. So yes, I mean, we can take the middle of the clay layer and see what was the initial effective stress, what is the final effective stress after load application and after dissipation of this load with depth. See what sort of range of effective stresses we are dealing with, and then choose an m sub b value, plug that in here, and then h is the initial thickness of the clay, that's 7.5 meters. Delta sigma, well, the change in total stress that can be calculated. Let's say the effect of change in a stress on the ground level at the center of the clay layer, and then that will give us a value, and that will be the settlement. However, this is not really precise. This is not really accurate. Reason is that the clay layer is just too deep. It's 7.5 meters deep, 7.5 meters thick. And well, yes, whilst this equation offers a very rapid solution, it's not ideal, it's not really accurate. So what instead we need to do is to split this clay layer into a number of sublayers and then calculate the consolidation settlement for each of these sublayers and then add them up. This will increase the precision of our analysis. So we are going to make use of a summation method. The thickness of the compressible layer or the layer which will face consolidation. The clay layer is 7.5 meters. We consider this thickness and we divide up this layer into a number of discrete layers. The thickness of each discrete layer will be delta H. So I can say that my consolidation settlement, my total consolidation settlement, will be equal to the sum of all m sub v's, which are multiplied by thickness of h sublayer, which is multiplied by the change in the effective stress or total stress. Let's use effective stress at the center of that sublayer. Depending on the number of sublayers, we will have a number of settlements and then we'll sum them up. We will add them up together to get the total final consolidation settlement. And this is our strategy. Obviously, all sigmas are sigma v's. They are all vertical values. So let's have a look to our clay layer. It's 7.5 meters thick. It's quite thick, and I'm thinking in a way to divide my layer into a number of sublayers which have similar thickness. Let's say if I go for a thickness of 1.5 meters, then mathematically I will end up with 5 sublayers. So let's begin. So the first sublayer like this, second sublayer, third sublayer, fourth sublayer, and fifth sublayer. Again, not to scale. So I'll have 5 sublayers, sublayer 1, 2, 3, 4, and 5, and the thickness of each sublayer will be 1.5 meters. The thickness of each sublayer will be 1.5 meters. Can I report this in a tabular form? Yes, I can. So let's use the word sublayer. And let's give my sublayers a name. So sublayer 1 2, 3, 4, and 5. These are sublayers 1, 2, 3, 4, and 5. I can say that the thickness of each sublayer, that's delta H in meter, is 1.5 meters. Ditto. I can say that the depth of each of these sublayers below the top of the clay soil, so the depth below the top of the clay soil is, let's use Z here. Z is, well, 0 to 1.5, then 1.5 to 3, 3 to 4.5, 4.5 to 6, and 6 to 7.5, the bottom of the soil profile. I'm going to buy a bit of space. Okay. How about depth to the center of each sublayer? Again, in terms of Z, well, we'll have 0.75 half height. Then we will have 1.5 plus 0.75, 2.25. These are the distance of the middle of each sublayer to the top of the clay layer. We are going to use that because the middle of each sublayer is a good representation of the entire sublayer. And we will do our consolidation analysis, our settlement analysis, always for the middle of layers and sublayers. So these values will be used later on. 3.75 for sublayer 3, 5.25 for sublayer 4, and 6.75 for sublayer 5. The distance between the middle of each layer, each sublayer, to the top of the clay. And I've indicated the middle of each sublayer with a red dot. Right. So now I have a number of sublayers and I can do my consolidation analysis for each of these sublayers to determine the delta H, the consolidation settlement, which impacts each of these sublayers for, well, each of my 5 sublayers. Right. What I need to do is to determine the delta sigma, or the effect of change in total stress, the effect of change in, let's say, the effective stress event at the ground level, right at the point of interest, which is the middle point of each sublayer. To do that, I need to begin with the initial effective stress at the center of each sublayer. So what I really need to do is to determine the initial effective stress at the center of each sublayers, and then to calculate the change in effective stress at the center of each sublayer, and then consider the initial effective stress and the change in effective stress to calculate my final effective stress, again at the let's say center of each sublayer. So that is my strategy. Needs a little bit of repetitive analysis, long repetitive analysis, but that is what we are going to do. As an example, I will do the analysis for sublayer 1. So for sublayer 1, in a different color, probably blue, I have sigma dash naught for sublayer 1, or let's say point A, which is in the middle of sublayer 1, is equal to, well, sigma, initial sigma at point A minus pore water pressure, initial pore water pressure at point 8. Now remind you that the water level is standing, we don't have a seepage problem, so pore water pressure is simply speaking equal to gamma W ZW. Total stress at point A in bracket. Right, so what do we have? It's the initial stress. Nothing has happened, no construction has happened, so we are dealing with initial stress values. I can see that I have, if you look into the diagram, I have 6 meters of unsaturated sand, and then I have, I think what it is, 3 meters of saturated sand. Yeah, so 6 meters of unsaturated sand, and I have 3 meters of saturated sand. And then I have different, let's say, heights, depending on the sublayer, different heights of saturated clay. Now, since I'm only interested in sublayer 1 for now, I have 0.75 meters of saturated clay. Let's begin from top and then go down. We will begin with the unsaturated sand. 6 meters of unsaturated sand multiplied by gamma of unsaturated sand. I have the bulk density of unsaturated sand, and this needs to be converted to unit weight. So I have 1976 kilogram over meter cube. If I multiply this by 9.81, that is the g, gravity acceleration, I will get Newton over meter cube, but then Newton over meter cube is not a good dimension, so another 10 to minus 3 to get kilonewton over meter cube. So I've got 6 times this expression in kilonewton over meter cube. So 6 meters times this expression, kilonewton over meter cube, will be kilonewton over meter square, or kPa, and I will be happy with the dimensions. Plus, I have 3 meters of saturated sand, so 3 multiplied by unit weight of saturated sand, 2138 kilogram over meter cube, times 9.81, that's g, gravity acceleration, Newton over meter cube, times 10 to minus 3 kilonewton over meter cube. All good. Plus, going down into the clay layer, I have 0.75 meters of saturated clay with a saturated density of 1920 kilogram over meter cube, which needs to be multiplied by 9.81 g, gravity acceleration, and 10 to minus 3 to convert the units from kilogram over meter cube to kilonewton over meter cube. And this is my total stress at point A. Total stress minus pore water pressure. Pore water pressure where? At point A. Pore water pressure is gamma W ZW. Gamma W is 9.81. You see, you can either use 10 or 9.81. The question is not asking you to use 10, and that's why I'm using 9.81. But you can feel free and use 10 as a simpler number. So 9.81, that is gamma W in kilonewton over meter cube, multiplied by ZW, the depth of water. Look into the diagram. The depth of water at point A. You have 3 meters of water inside the sand layer and half height of the first sublayer inside the clay layer. Half height, the first sublayer, is 1.5 divided by 2, 0.75. So 3 plus 0.75. 3.75. So your initial effective stress at point A is equal to 157 kilopascal or kilonewton over meter square. That's all done. And you can do the very same analysis for sublayer 2. So if you take point B as the point in the middle of sublayer 2, I will speak less because this is something as of repetition of first part, minus UWB, that will be equal to again 6 times 1976 times 9.81 times 10 to minus 3. That is the unsaturated sand plus 3 times 2138 times 9.81 times 10 to minus 3. This is the saturated sand plus, now instead of 0.75, now you have 2.25. 2.25 times 1920 times 9.81 times 10 to minus 3, and that is the total stress inside the saturated clay soil at the very last term, minus pore water pressure. Again, gamma W, 9.81 kilonewton over meter cube, multiplied by the depth of water at point B, which is 5.25. 3 plus 1.5 plus 0.75, which will be 5.25 in meters. So your initial effective stress at point B, which is in the middle of sublayer 2, is equal to 170 kilonewton over meter square. And you've got to repeat this let's say, analysis to get the initial effective stress at the center of each of your sublayers, and then report this in a tabular form. Now, in addition to the initial effective stress, what you need to do is to determine the change in effective stress in the middle of each sublayer. So let's see how that works. I have a rectangular raft foundation. I have a rectangular raft foundation. And my rectangular raft foundation is 27 meters long and 18 meters width. And well, I need to determine it is under certain amount of net stress. So this is your net stress. Evenly distributed. This is your net stress, or the stress at the bottom of the excavation, at the bottom of the excavation, at the bottom of your foundation. And you have a number of sub-layers, and you do need to calculate the effect of this net stress, or how much of this net stress remains at the center of each of those sub-layers. So you have basically a distance from bed of the foundation to the center of each sublayer. The first center, that's point A, then point B, then point C, then point D, and then point F. Each of these points have a distance from where they are and the bed of the foundation. Now we know how to make use of the Steinbrenner method. And we know the limitation with the Steinbrenner method. The limitation with the Steinbrenner method is that the method only offers you the degree of stress at the corner of your rectangular, let's say, loaded area or surcharge area. And to go around this problem, what we normally do is that we split the surcharge area into 4 smaller areas, area 1, 2, 3, and 4, and we determine for each of these areas, we determine the value of stress at the point of interest and at the corner of that sub area. And we repeat this 4 times, or we multiply this value by 4 to get the total value of net stress at the point of interest after dissipation with depth. And this is, again, our strategy. Now, the Steinbrenner method is clear. For the Steinbrenner method, well, you have 5 layers. So let me put together a table. So sublayer 1, 2, 3, 4, and 5. In fact, I have points A, B, C, D, and F, which are at the center of that sublayer. So really center of your sublayers. So you have point A, you have point B, you have point C, you have point D, and you have point F. And then what you are after is the change in effective stress. The change in stress or the change in effective stress at these points. How you can get this change using the Steinbrenner method, which needs a coefficient known as I sub q. To get this coefficient, you do need to use a table or a diagram which relates this coefficient with B over Z and L over Z. B is width, L is length, and Z is depth. So this is pretty much my strategy. And I know that the delta sigma dash, when I calculated my I sub q will be equal to, in green, will be equal to I sub q multiplied by not delta sigma, the total value of surcharge which is applied to the foundation, but the q sub net. So I've got to calculate the q sub net as well. Also, I know that this is not enough. Either I've got to do this analysis for each of these sublayers, or to do this analysis for one sublayer and multiply my delta sigma dash by 4. This is what I'm going to do because that will save a lot of time. So the first step, q sub net. How can I get my q sub net? Q sub net is the stress at the bottom of foundation. Q sub net is equal to the surcharge, 250 kPa. This is the surcharge which is applied to the foundation from the superstructure, minus the effect of excavation. Okay, so how much excavation I'm talking about? 3 meters of excavation. And 3 meters of excavation into what type of soil, with what unit weight? Well, I know the density of unsaturated sand, which is 1976 kilogram over meter cube. Again, kilogram over meter cube. I do need to convert kilogram to kilonewton. Kilogram to newton times 9.81. Newton to kilonewton times 10 to minus 3. So all sorted now. I have kilonewton over meter square here, kilonewton over a square here, and Q net is equal to 157 kPa or kilonewton over meter square. You can see how far you have managed to reduce the surcharge to the net stress by excavation. Obviously, it comes at a cost. 3 meters is a lot. You're probably talking about 2 to 3 levels of basement, 2 to 3 levels of, I don't know, underground parking or a commercial kind of underground floor. But you can see how it can help you in terms of reducing your net pressure, net stress, and eventually your settlement. So it comes at a cost, but it has some benefits. Now let's look into our table. I'm going to make use of black color. B over Z. Mind you, I am making my analysis for each of these smaller sub areas. So my B is the width of the sub area, and my L is the length of the sub area. So L and B. I'm talking about sub areas. And Z is the distance between each of these points of interests and the bed of the foundation. So let's begin. For sublayer 1, for the middle of sublayer 1, point A, B is, well, 18 divided by 2. And Z is, you have 6 meters of sand plus the distance between the boundary between sand and clay and the middle of your first sublayer. Each sublayer is 1.5 meters. So the middle of each sublayer worth 0.75. So 6 plus 0.75. You can look into your diagram and see where this number is coming from. Now this is equal to 1.33. How about L over Z? Different color. Let's say blue. L is 27 divided by 2. And Z, same value, 6 plus 0.75. Your L over Z is 2. Now, if you look into your charts, into your tables and diagrams, you will see that your I sub q is equal to 0.216. You can either use linear interpolation if you are moving between numbers, or you can be conservative and go for the maximum maximum I sub q for the numbers that you have. Between 4 numbers, you can go for the maximum value, but that is really the conservative design. Now that I have my I sub q, my L over Z, and B over Z, I can plug these numbers into the equation and get my change in effective stress in the middle of sublayer 1. That is I sub q, 0.216, multiplied by q sub net, 157, multiplied by 4. To use your calculators, you will get 135.65. Now, I've done the analysis for all soil layers. I'm not going to repeat them here in front of you, but you can do it at home and check your numbers against mine. And I'm going to write these values here for you. For sublayer 2, I have 1.09. For B over Z, 1.64. For B over Z, 0.201 for I sub q. And I can tell you that I sub q's that you have here are determined through linear interpolation. As I said, you can feel free to do a conservative design. I have done linear interpolation. And delta sigma dash is 126.5. For point C in the middle of sublayer 3, 0.92, B over Z, 1.38, L over Z, 0.183, I sub q, and 114.92 delta sigma dash. Next, 0.8, 1.2, 0.168, and 105.5. You can see how the change in effective stress because of surcharging, or let's say the effect of surcharging on change in effective stress, is reducing as you're going down into deeper depths. This is how stress dissipates. Lost, 0.70 B over Z. And finally, delta sigma dash, 93.6. Everything in kPa throughout. So let's do a summary table. I have a number of sublayers. Sublayer 1, 2, 3, 4, and 5. I managed to calculate the initial effective stress at the center of each sublayer in kilonewton over meter square. That's the beginning of the solution, and I'm going to write these values here. It's a summary table. 184, 197, and 211. I also managed to calculate the delta sigma. In the middle of each soil layer. And these were 136, 126, 115, 105, and 94. So the final effective stress in the middle of each soil layers will be equal to the initial effective stress plus the change in effective stress these will be 293, 296, 299, 302, and 305. I think I have all I need. With an exception of M sub v, I still don't have the relevant M sub v for my different stress levels, and you can see that for each sublayer the stress is changing from the initial effective stress to the final effective stress. So what I can do is to determine the average value of the stress in the middle of each sublayer. So the average value of effective stress in the middle of each sublayer will be 225, 233, 241, 249, and 258. Now that I have the average values, I can look into my diagram. M sub v versus sigma dash, or my table, and choose the relevant values of M sub v for each average effective stress. Or again, you can be conservative. If these values are falling in a bracket in your table of M sub v versus sigma dash, you can go for the larger number of M sub v. It's up to you. But since through all this exercise, I'm being precise, I'm trying to be accurate, I have done linear interpolation and I will report the true numbers here. So M sub v in meter square over kilonewton will be equal to 235 times 10 to minus 6, 229 times 10 to minus 6, 225 times 10 to minus 6, all of them in meters square over kilonewton, 220 times 10 to minus 6, and 215 times 10 to minus 6. Delta H, consolidation settlement, is equal to the sum of all consolidation settlements for each of these sublayers, M sub v for layer I multiplied by the thickness of sublayer I multiplied by the change in effective stress at soil layer, let's say I. Let me show you how each of these values match the values I have here. So for soil layer 1, M sub V is known. The thickness is, well, 1.5 meters. And the change in effective stress is also known. So I can determine the consolidation settlement for each sublayer and sum these up. The consolidation settlement will be equal to top to bottom, sublayer 1 to sublayer 5. You can use your calculators and double check. 0.0484 meters plus, and that is soil layer 1. 0.0433 plus 0.0385 plus 0.0343 plus, for the last sublayer, 0.0314. Again, interesting stuff. You can see how the consolidation settlement for each of these sublayers is reducing as the depth is increasing. It's because of stress dissipation. Your total settlement will be equal to 0.1959 meters or 196 millimeters.